Hello, my name is Kaustubh Simha. I'm a first year, and I'm working with Sean Doan, who's a fourth year, and our project is doping quantum materials. First, let's give a brief introduction on semiconductors and doping. Semiconductors are materials, like silicon, that are the backbone of today's computing. These materials have electronic properties that fall right between a metal and insulator. And doping is a process of either adding electrons, negatively doping, or taking away electrons. And this process combined with semiconductors makes them really, really powerful. One of those uses is actually seen in a critical digital logic component called a transistor. A transistor is basically a piece of semiconductor that is partially doped. It is the building block of all logic components in today's day and age, and your phone probably has about 2 billion transistors. In our project, we plan on making these transistors using atomically thin materials. Um, and for our base semiconductor, we plan on using tungsten diselenide, monolayer, and for our positively doping agent, we plan on using ruthenium chloride. The importance of our project is really important because by using atomically thin 2D materials, we can make much smaller transistors than the conventional 5 nanometer thick silicon. This allows us to fit way more of these in a certain area, which means we can have more computational power in our everyday devices. Also, the materials we plan on using are very easy to maintain, fabricate, and extract. So, so here's actually a picture of our sample that we got a chance to take some photoluminescence and Raman spectroscopy measurements. This triangle is actually the base tungsten diselenide that's partially covered by the ruthenium chloride. And here's actually the results of our measurements that we took at 3 Kelvin just to make sure that the phonon interactions are at a very minimum. So you could, from the purple and the orange, the purple being the undoped region of this tungsten diselenide and the orange being the doped region, you could see a drop in the exciton peak, which shows us that our that the that there's big doping is involved in this region, as there's more holes being formed, so there's more trions, and the exciton number is being limited in our doped region. And the step two of our process, right before we get to the transistors, is to make a device that can take transport measurements on tungsten diselenide. Here's actually two of three stacks that we have set up for this device. And what we plan on doing in this device is actually having a encapsulated with HBN, ruthenium chloride that's covering monolayer tungsten diselenide. And through this, we plan on putting contacts right between the ruthenium chloride and the WaC2 and performing transport measurements, just like the infamous transport measurements on graphene, like the Hofstadter butterfly and the quantum Hall effect, and to see these really cool quantum effects that happen in graphene in tungsten diselenide, which has never been done before. And for the final step of our project, we plan on making a transistor. This is actually a PNP transistor demo, the ruthenium chloride being the positively doped side, and some arbitrary negatively doping agent. It doesn't have to be too strong because it's the base of the transistor. And yeah, and then we plan on taking electric measurements and seeing how the change in voltage and all that actually affects this device. Here's our credits, and thank you so much.